First, I will use the code we worked on last time as it is, without any modifications. From here, we will proceed to the packet header, and then we will create a command to check if the packet is indeed accurate, extern full packet check, and then fire. So add the SD and then copy this. First, at the very end, return true. First, check the STX, ETX, N, CMD and checksum. Here, if the first byte is not STX, it will fail and return false, ending the process. Honestly, the Arduino IDE is a bit inconvenient, so in my case, I usually use Visual Studio Code for actual development projects. For now, I'll just try it out. If the last byte, length 1, is not ETX, it will return false. To elaborate, when you add the SD, make sure it is properly formatted and compatible with your system. Copying this step ensures that you have a backup in case something goes wrong. Returning true at the end signifies that the process has been completed successfully. Checking the STX, ETX, N, CMD and checksum is crucial for verifying the integrity of the data being processed. If the first byte is not STX, it indicates a problem with the data stream, causing the process to fail and return false. The Arduino IDE, while functional, lacks some advanced features, which is why I prefer using Visual Studio Code for more complex development projects. Trying it out now will help identify any potential issues early on. If the last byte, length 1, is not ETX, it means the data stream is incomplete or corrupted, leading to a return of false. It was the length, but if you look here, there is STX, and, then len, and, after that, there are other bytes. In the case of len, it was about entering the length of everything, except for STX and lan. So this was the total buffer length minus 2 at that time. So if we are going to convert the buffer length based on this, when we add 2 to the length, we get the total buffer length. Therefore, we add 2 here. If the MAC is simply different from the variable, just return false. This is how it is structured and organized. Next, the switch shot data, which includes the value B, and B was the command byte, is now referred to as PCMDA, meaning that the data has been updated Please provide specific instructions to command the bot to ensure it performs the desired actions accurately. We did it this way. And as you can see, we first divided the commands into A, B, and C. This division was crucial for the subsequent steps. So if any of these A, B, or C is caught, it enters here and exits the switch statement. This mechanism ensures that the process is streamlined and efficient. If nothing is caught, it goes to the default case and ends with a return false. This default case acts as a safety net, ensuring that the system behaves predictably. This is how the verification is set up. The verification process is designed to be thorough and comprehensive. Next, we input the build Polky GS shop. Data first. Because the last part is CS, just like we did last time. This step is essential for maintaining consistency in our process. Then we calculate the CS here in the same way, and check if the calculated value matches the byte at the specified position. This final check is crucial for ensuring the accuracy and reliability of our results. Have we done this far? So now, if there are no issues, let's proceed to do this exactly the same way as before. We'll generate the necessary components here, remove the buffer part that is not needed, and then perform a serial println operation. After that, we will print the check packet to ensure everything is correct. Following this, we will check the packet with an if statement to verify its integrity and correctness. This process ensures that all steps are followed meticulously and no errors are introduced. By doing this, we can be confident that the packet is accurate and reliable. So, if you do it like this with serial println, which is a method used to print data to the serial monitor for debugging purposes, then of course the check packet, which is a small data packet used to verify the integrity of the data transmission, has been created accurately and without any errors here. After creating it accurately, we now buff it here, check it, and if it returns true with no issues, then it will show OK. Otherwise, I will try to fail it once. As you can see now, the check packet shows OK. Shall we test it again? If you intentionally manipulate the data for testing, let's see how it works with the checksum in place. Let's change it to 0xA while it is in the state of having a checksum in the current context, and also upload it, and it appears like this. This time we have created a command to check the check packet. In the next session, since we have verified it, we need to pull the data. So now, based on the verified check packet, we will look at what the command is, how long the data inside it is, and create a command to extract the data. Then I will see you next time.